GCSE Physics boosters, half-life. There's Gordon Freeman. Tell us about half-life, Gordon. Well, right now, what are the chances of rolling a 6 on a dice? Okay, obviously 1 in 6, a sixth. If you rolled a dice 6 times, would you definitely roll a 6 once? And the answer is obviously no. Now, why? Because rolling a dice is a random process. It's all to do with probability. We know what the probability of rolling a 6 is, but that doesn't mean if we roll a dice 6 times, we're only going to get 1 6. We might not get any 6s because it is random. Now, here's an unstable nucleus. Okay, at some point in the future, it's going to decay. And that's basically, imagine that's like rolling a 6. At some point in the future, you're going to roll a 6, but you can't predict when it will decay, because radioactive decay is also a random process. You know, you can hit it with a hammer, you can stick it in a Bunsen flame. Basically, you can't affect it. Okay, radioactive decay is a random process. It is governed by chance. What you can say is the probability that it will decay in a certain time, just like a dice. So if you have lots and lots and lots of dice, a very large number of dice, and you throw them all, then about 1 out of every 6 of them will land on a 6. About 1 out of every 6th. I'd be very surprised if it was exactly a 6th. The larger the number of dice, then the closer the fraction will be to a 6. Because it's random, then all of these fluctuations will cancel, and the larger the number, the closer and closer the fraction will be to a 6th. So if you have a very, very large number of unstable nuclei of a particular isotope, now, we can predict how many will decay in a certain time. You know, we might not predict to the individual atom, but we will know what fraction of them will decay in a certain time. We can also predict how long it will take for half of them to decay. And the time it takes for half of them to decay is called the half-life. It's the half-life of that isotope. So any particular isotope has a particular half-life. This is an isotope. It's radioactive. It's called americium-241, named after America. It's used in smoke alarms. It gives off alpha particles, and if smoke gets in the way, then it affects the number of alpha particles detected. We're going to talk about it in another video. It has a half-life of 432 years. And that means that in 432 years, there's a 50-50 chance that one of these atoms, or rather one of the nuclei of the atoms, will decay. In 432 years, the number of atoms of that stuff will halve. And the count rate, or the activity, you should know the difference between those two, of the sample will halve. So basically, if you buy a smoke alarm, it will last you the rest of your life anyway. Your great-grandchildren can inherit it. It will last a long time. Now, an experiment you should know is how to measure half-life. And one of the ways to do it is using something called protactinium. Now, it's a little bit complicated. Don't worry too much about it, but there's this isotope of uranium produces the protactinium, and the protactinium floats in oil. So you give the tube a shake, and then the oil floats to the top, and you've got your protactinium at the top. And the protactinium has quite a short half-life. So what you do is you can measure the number of counts, for example, every 20 seconds. And as time goes by, the number of counts every 20 seconds should go down as the protactinium decays. And then you can plot a graph and you can work out the half-life. what will the graph look like? It'll look like this. Okay, and this is called a decay curve for the decay of protactinium. On the y-axis, counts in 20 seconds I've got. On the x-axis I've got time, and this shape, this curve, it's called an exponential decay. In A-level physics it pops up every now and then. One thing you should do actually before plotting your results is take a reading of background radiation for 20 seconds and then subtract that from all of your measurements. Okay. Notice as well that not all of the points fit the curve. We've done a curve of best fit, but not all the points fit it. Why? Because radioactivity is a random process. Now, in an exam, one thing you're very likely to be asked to do is to get the half-life from this graph. So if we're starting at 200, how long does it take to get to 100? And with a ruler and a pencil on the graph, draw a couple of lines. It takes 70 seconds. You don't have to start at 200. You could go from 160 to 80. You could go from 120 to 60. You could go from 80 to 40. The half-life should be the same every time. So you should be able to get the half-life from a graph like this. Let's finish with a couple of questions to see if you understand what half-life means. Have a go. I'll show you the answers in 3, 2, 1. There. So the first one, a GM tube detects a count rate of 800 counts per minute. A rock that contains an isotope with a half-life of 12 minutes. So what will be the count rate after 24 minutes? Well, that's 2 half-lives. So the count rate will halve and then halve again. So 800 to 400, 400 to 200. 200 counts per minute. The second one, a sample of a radioisotope has an activity of 4,000. After 6 hours, the activity is 500. So how many half-lives? Well, 4,000 to 2,000, 2,000 to 1,000, 1,000 to 500, that's 3 half-lives. So if 6 hours is 3 half-lives, then a half-life is 2 hours.